Hi everyone and welcome to Microchip's Shields Up webinar series. My name is Megan Walton and I'll be walking us through some quick housekeeping items before we get started. Be sure to visit our Shields Up webpage, www.microchip.com/shields-up for more information on upcoming sessions. I'd like to now introduce our presenters for today. First we have Nathan Studer, Senior Engineer with the SEL4 Technologies Group at DornerWorks. Nate has over 15 years of experience in FPGA and embedded software engineering, including microkernel operating systems and virtualization. He has been the primary investigator on several DARPA SBIRs attempting to leverage formal methods, virtualization, and microkernels to improve security of embedded systems. Next, we have Tim Marin, Technical Fellow at Microchip Technology in the FPGA Business Unit. Tim has over 30 years of experience in marketing and engineering within the semiconductor and defense industries. Over the course of his career, Tim held numerous engineering and marketing positions at Texas Instruments Defense Electronics Group, Atmel Corporation, Microsemi Corporation, and now Microchip, where he's responsible for defining and bringing new products to market for the FPGA business unit. And lastly, we have Jesse Millwood. Jesse's been a part of DornerWorks SEL4 Technologies Group for the past 4 years. Through his group, he has been able to present on using SEL4 with RISC-V at the 2019 RISC-V Summit, as well as contribute back to the upstream SEL4 kernel and libraries through various SBIRs where security and virtualization have been the main focus. Today they'll be covering session number 22, Enabling Device Security with a Formally Verified Microkernel. Without further ado, I'll turn the presentation over to Nathan. Thank you and enjoy today's session.
Thank you to Megan for the introduction, and thanks to our attendees for joining today. I'd like to start with just going over the agenda briefly. We're going to talk about the problem and some things to help address that problem in the form of microkernels and formal verification, and interesting technology, SEL4, which combines these two in the form of the first microkernel with a formal proof from specification to implementation. SEL4 has recently been ported and verified on RISC-V and ported to the PolarFire SoC, which we're going to demo and then give some links on how you can get started using SEL4 and PolarFire SoC in your products. And the problem is one that we're all familiar with. We want to know, is our application secure? And the traditional way that we go about this is we maybe do some type of waterfall development, design it really well, test it a lot, hire a red team. If they find anything, fix it, hire the red team again, fix it again, and just repeat this cycle until they don't find anything worth fixing. And once we're done, we just hope that there's nothing left out there to be found in the open. And history has shown us that this is not the case. There always is bugs found after production. So there has to be a better way. And lots of answers have been proposed. The two, with the third being SEL4, provided in this presentation, are some of those. These two that we're going to go over are not new in any way, but they've been a bit reinvigorated by the increasing need for security today. And the first that we're going to talk about is microkernels. And this is going to be a very whirlwind introduction, given mostly as a contrast to the traditional monolithic kernel. In a monolithic kernel, everything that needs any type of privilege exists in the same privilege domain as the kernel itself, whether that's the file system, virtual memory, the scheduler, device drivers, and all that together into one binary provides a very large privileged attack surface for hackers to attempt to penetrate. Whereas in a microkernel, we try to simplify and modularize and get rid of everything in the kernel except the bare minimum that's needed. That usually boils down to some interprocess communication, some virtual memory, scheduling, and we push everything else out in the user space. And the most important thing that we're pushing out to user space, in my opinion, is the device drivers. Because while often we can secure our kernel pretty well, we frequently need to interact with third-party code or third-party device drivers or user devices, and giving them a straight shot to the kernel is problematic from a securities perspective, and microkernels can prevent that.
Hey Nathan, sorry to interrupt, but I got a quick question. I've heard that microkernels are, you know, kind of slow, but they have really good security. Can you comment on that?
Yeah, Tim, you hit on exactly what I was going to cover, which are the main strengths and what has in the past been a weakness of microkernels. Splitting things off into their separate threads makes everything small and compact, kind of easy to verify on its own, and makes all the threads very isolated from each other, so that if something goes wrong in one thread, it's unlikely to be able to affect other threads. And since all these threads are separated from the kernel itself, it's unlikely that any thread can attack the kernel. But adding all these threads to the system does mean that there's a lot more complex process management going on, and we have to undergo a lot more context switches than we would have in a monolithic system. And this context switching was one of the primary drivers of the performance overhead of microkernels in the past. However, the modern generation of microkernels running on modern hardware with a lot of address space identifiers can be shown to have similar performance on applications to their monolithic cousins.
Okay, so a microkernel, specifically, you know, SEL4, provides the advantages of security, and modern-day architectures with large memory pools kind of like fill the gap for performance.
Yes, and the primary goal of SEL4 when it was developed was not to sacrifice performance for security. And so with that being the primary goal, it was front and center, and they have published several benchmarks that show that they are very competitive with other options.
All right, thank you.
So briefly, we move on to formal verification. Formal verification as a branch of formal methods. And formal methods are a way of rigorously defining a system using mathematical models. And once we have a mathematical model of a system, anyone who's taken geometry knows that we can write proofs about it. But why would we want to do that? So take, for example, we might have a requirement in our system that says one thread cannot write to another thread's data without permission. This would just be a standard kind of integrity requirement. If we wanted to test that requirement, it would be very difficult. We could hire the best tester we want, we could have the best code coverage tools, and even then, it'd be hard to be certain that we had actually covered every possible path. Whereas with a formal mathematical model, we can write a statement such as, there does not exist a path through which one thread can write another thread's data without permission, and we can prove it, which is really where the power of formal methods shows up. How would we go about doing formal methods? Well, there's no one way. There's many ways to do it. We show one possible way to do formal methods on this slide. It happens to be a very gross simplification of the way that SEL4 was verified, but there are many other ways that can be done. In the first step, we describe the system in a modeling language that we can reason about. And in the next step, we can write proofs about this system. The modeling language that we write the description is usually not fit for running on actual hardware. So somebody needs to then implement it in the actual in a format that's compatible with real hardware. Usually that ends up being C. And often the verification and the implementation are kind of done separately, and they come together at the end. And the Data 61 in developing SEL4 did something really neat where they had verification and implementation going on at the same time, which makes a lot of sense because there's some things in C that are intractable to verify, and there's things that are easy to verify that would make absolutely terrible software. So working out a compromise between the two is how SEL4 was able to maintain the performance it did while also being able to verify it. And then the last step is that once we have proofs on our formal model, we need to show that that the same proofs apply to our C implementation. And to do that, we have to do a refinement step to show that the implementation is an embodiment of the formal specification, which sounds easy, but it's quite difficult and requires, in this case for SEL4, the formal semantics of a subset of the C language, which in itself is a major undertaking. As I mentioned, the strength of formal methods is primarily in being able to prove things that are difficult, if not impossible, to test. But there's also some side benefit in having to precisely write down what your system does, because that can help avoid things such as vague requirements or contradictory requirements, which just about every engineer has had to deal with before. The weaknesses have been that formal methods are generally quite difficult to use. There's a lot of research that's being done to try and make them more accessible to the everyday engineer, and a lot of it's very promising, but still it's kind of a very niche field, which in general means it is more expensive. However, metrics on the SEL4 development show that formal verification can be only a couple times more expensive than low assurance test-based verification. And if we factor in the maintenance cost of bugs found after the fact, there is probably doing formal methods up front might be a good investment even in low assurance scenarios, especially if we can focus our expensive formal verification on the modules that are most important for the system security. And which part of the system is most necessary for security? Well, the kernel, on which just about every software on top of it depends, which is where the idea from SEL4 came from, in which Data61 developed and created the first microkernel with a formal proof from specification to implementation. And it is a microkernel. It has the exact architecture we showed previously. It's very small, less than 10,000 lines of code. But Data61 didn't just develop a microkernel. They didn't just develop a straight microkernel. They also added some innovative features, such as the multiple criticality scheduler and capability-based security, which is an alternative to access control lists that deals with some of the problems with that means of privilege control. And as I mentioned, they have provable isolation of the threads and very high performance interprocess communication, since performance was a primary goal of the project.
Hey Nathan, I've got a quick question. I mean, security means different things to different people, and the definition of security is not consistent throughout industry or in various localities, like maybe North America versus Europe versus Asia. Now, I know from a North American perspective that there is some concern about where things were developed. So I understand that the original SEL4 kernel was developed outside of the U.S. And for those super critical security conscious customers in North America who are concerned about origin, and the same thing applies to European our European counterparts and even our Asian counterparts. Everybody's really concerned about where were things sourced, right? How does SEL4 address those concerns?
Yeah, you're right, Tim, is that SEL4 was originally developed by NICTA and is largely maintained these days by Data61, which are both Australian firms. The first way to mitigate that is that they are open source products, so they have many contributors and many eyes. So if there was something untoward in the verification or the source code, someone could find it, and anyone who is concerned could look at it. Right. Additionally, there are a number of U.S.-based services firms that are now specializing in SEL4 services. And recognizing the same concern that you had, Tim, DARPA has banded together a group of these companies, including DornerWorks, IAI, Critical Technologies, and some others, into a SEL4 Center of Excellence to provide US-based training, development, maintenance, and support of SEL4, which should help alleviate some of those concerns.
Thank you.
Moving on, there's been a number of things proved about SEL4. The standard security properties of integrity, confidentiality, separation, kernel proof for Mills-type applications. We're not going to get into all of those, but the one that's interesting to note is the kernel binary code proof, which on some platforms shows that the binary code correctly implements the C semantics, which is a fancy way of saying that you can use an off-the-shelf compiler and be certain that it hasn't inserted a binary Trojan, which is important for security. Or equivalently, you can say that all object code can be mapped back to source code, which is an important consideration in safety certification as well. The functional correctness proof itself bears some looking into. The complicated statement of what it means is that the binary code of SEL4 correctly implements the behavior in the specification and nothing else. But what it implies is quite powerful. It implies that all kinds of normal kernel programming errors are just gone. And we recognize these errors because they show up all the time in the CVEs. So their absence really speaks to the security of the SEL4 microkernel.
I have an additional question. Is it fair to say then, since this kernel is formally verified, and you know, in the previous slide you list all these common programming errors that lead to zero-day exploits, right? Right. Is SEL4 zero-day exploit proof? The kernel itself?
That would be going too far. It is proven to meet its specification.
Right. Yeah, that gets back to any kind of security scheme can be broken given enough time, energy, and money, right?
Yes, but given the proof, it's very unlikely that there would be such an exploit.
Right. All right. Thank you.
The SEL4 has been ported to a number of platforms, such as x86 and ARM. Some of these platforms have the proof done all the way to the C implementation, and others have it done all the way to the binary. Platforms that have the proof done to the binary are called proven platforms, or at least we call them that. And RISC-V is one of those. And in fact, RISC-V with its OpenSS IFA has a very interesting target because due to the open IFA and the open nature of some of the RISC-V implementations, it might be possible to someday extend the proof across the hardware-software barrier. Now that sounds great, but what can I use SEL4 for? Can I use it for my desktop? Well, no. Currently, there aren't the normal libraries and utilities that most users would expect to have on a desktop system to run SEL4. Can I run ARINC 683 or FACE or SOSA open architecture applications? DornerWorks those APIs currently don't exist, but DornerWorks and several other companies are working hard to make those APIs available. However, there is some difficulty with implementing the POSIX interface because it's not a good model for microkernels, but it is possible to implement a subset. So if anyone was interested in that, feel free to reach out and contact us. And that gets us to what SEL4 is intended for, is highly secure embedded systems. And
so quick question, Nathan. So if I use SEL4, I mean, does that actually make my system secure? I mean, what additional things would I need to do to button it all up?
So yeah, so SEL4 only covers one aspect of security. Security is obviously a system level thing. There's hardware security, supply chain security, application security, everything. And while SEL4 provides a great base for the software side of things, and platforms such as the PolarFire SoC can provide a way to meet the hardware requirements, the end system security is up to the system integrator. Of course, DornerWorks and Microsemi are available to help customers that would like to leverage these type of technologies in the appropriate way to get the most security benefit out of both the PolarFire SoC and FDL4. And since I mentioned PolarFire SoC, that makes a great transition to Tim talking about the PolarFire SoC and the Icicle Kit that FDL4 has recently been ported to.
So really to kind of like button it up and continue the conversation a little bit, you know, DornerWorks has done all the hard work for, you know, porting a formally verified microkernel, which provides kind of a foundation for a user application to run on. But and then PolarFire SoC provides a secure hardware platform for cell SEL4 to run on. You know, we have built-in secure boot methodologies. As a matter of fact, you know, a previous Shields Up webinar, you know, number 12, went into some detail on how PolarFire SoC offers up a couple of secure boot methodologies. And you mentioned, you know, supply chain concerns as well. You know, we integrate and embed a X.509 digital certificate that's been signed during our manufacturing wafer sort and packaging test by some HSMs, which are, you know, effectively a cryptographically secure, you know, piece of hardware, and they're signed by the private key in these HSMs, and so we can provide some supply chain authenticity to our customer base. And, you know, the PolarFire SoC, you know, platform is been designed to be secure as a piece of silicon. So we've done things like we've chosen, you know, a 5-stage in-order CPU for the RISC-V CPUs that are Spectre and Meltdown immune. We have secure boot. We have side channel resistant, you know, programming methodologies, and in some devices we have side channel resistant crypto coprocessors. So PolarFire SoC is a platform you can build secure solutions on top of. DornerWorks has provided, you know, all the hard work for SEL4, and you can try all this stuff on the Icicle Kit, which is, you know, selling right now. You can buy it on the Crowd Supply website. Can you advance the slide, Nathan? It's a fairly inexpensive board at just under $500. We're shipping at the end of the month. You can just click on that link down there or just Google PolarFire SoC Crowd Supply and you'll get there. So, you know, customers, the end customers who use these hardware software systems, I think, Nathan, it's probably standard practice for them to do a risk assessment to actually really button up the security needed for their system. Without a proper threat analysis and risk analysis, it'd be very difficult to completely kind of like make that claim that my system is secure against these threats. Would you agree with that?
Yes, I would agree.
Yeah, okay. And so I think that now is, we're at a stage where we want to actually demonstrate SEL4. This will be a live demo, so hopefully the demonstration gods will favor us. And Jesse, please take it away.
All right, thanks. All right, so this is a simple TMUX setup that I have here that's going to be showing 4 of the 5 UARTs that are broken out from the board. We're going to have the HSS bootloader showing in the top left, the U-boot showing in top right, the SEL4 kernel debug will be in the lower left, and then the SEL4 test suite will be showing in the bottom right. So I'm going to turn the board on here. Here we see the HSS bootloader coming up on the monitor core. It's going to read my U-boot payload from an SD card, and I have the U-boot setup here is going to load my SEL4 image from the same SD card. So there's a lot going on here, and you aren't necessarily meant to be able to decipher this in real time right now, but what's happening is that there are a number of tests that run in user space and exercise all of the syscall wrapper APIs, helper library functions, and some basic hardware drivers. So many of these tests aren't necessarily dependent on the hardware, but it is still a good idea to make sure that a change somewhere didn't inadvertently cause an issue somewhere else, and that everything is more or less supported on your platform. So I've enabled a lot of the debugging printing here for the kernel and the test suite. So we've already seen some basic startup messages kind of came through in a waterfall text. So some of them are the result of the test suite setting up the runtime environment, and in SEL4 terminology, there's a root thread that receives all the permissions, doles out all the memory and capabilities to other threads, and then the test suite runs as this root thread and creates a virtual memory space, capability spaces, and handles other servers and all their permissions. So here we go. We have the all is well in the universe text. We passed all the tests that were for this platform. So,
thank you, Jesse and Tim, for that content. In summary, SEL4 provides a very secure foundation for high assurance or security-focused products. And it's both open sourced and has a formal verification proof. If you follow the link there, there's instructions to run the demo that Jesse just showed on the PolarFire Icicle Kit. And if you weren't able to get a hold of one of those kits, there's also instructions to run it on the Renode emulator. There's some additional links to learn more about the PolarFire SoC and to learn more about SEL4 at the Data61's website. Sorry
to interrupt, but so we've got SEL4 running on PolarFire SoC. So the hard part has really kind of been done. But where would customers go to learn actually how to write applications using SEL4?
Well, yeah, Data61 there's a lot of places. Data61 has published a good amount of material on their wiki, some videos, some blogs, excuse me. That gives content that users could use for some kind of self-paced training to learn how to write SEL4 applications. There's also an SAE training course that DornerWorks has put on that might be offered in the future. And also the previously mentioned SEL4 Center of Excellence puts on a training each year at their annual summit. This summit is coming up this November if anyone was interested. And as well, DornerWorks itself provides something that we call the SEL4 Quick Start package, which is some in-person training, or at least these days with the pandemic, a remote training along with some design consultation with SEL4 on your platform, or at least on a reference of your platform, which we've found to be a good firm fixed price option for customers that want to get started using SEL4 without a big investment or commitment.
Right, and I might add that DornerWorks is a Microchip design partner and is very familiar with our products and our tools, so they can get customers and our clients up and running in a very short order. Okay.
I just want to thank everyone for joining us today. We hope you found the session informative. You can also visit www.microchip.com/shields up to view all upcoming sessions and watch past presentations on demand. You can also follow us on LinkedIn, Facebook, Twitter, Instagram, and YouTube for the latest news and updates. Thank you, everyone, for your time, and we do hope to see you during our next session. I hope everyone has a great rest of your day.